Welcome to Module 2, which focuses on the Hare Hale framework and the story of two Detroit students who led a revolution in measurement. Statistical metrics such as Cohen's d often fail to motivate legislators, parents, or policymakers because the numbers sound small. Jim Hare, an education policy strategist, and Charles Hale, a mathematician and engineer, both attended Detroit public schools. They developed the framework to address the limitations of current educational measurement. The translation problem highlights that if a student is moving away from proficiency, even slightly, the time required to reach grade level is effectively infinite. Mathematics offers no answer for dividing a positive gap by a negative growth rate. The solution was not a new statistic, but a better translation. It converted abstract decimals like -0.59 standard deviations into a visceral, human-scale reality that policymakers could feel. The Hare Hale timescale is a powerful formula that converts any achievement gap and any growth rate into school years, a unit of time everyone can understand. Now let's explore the architecture of this formula that transforms educational data into relatable time units. The Hare Hale timescale formula calculates years to proficiency by dividing the gap in instructional days by the growth rate in instructional days. The numerator converts the gap to proficiency, measured in standard deviations, into instructional day equivalents by multiplying it by 720. The constant 720 represents the instructional day equivalents per 1.0 standard deviation, derived from the finding that 0.25 standard deviations equals 180 instructional days. The denominator converts the annual growth rate, measured in standard deviations, into instructional days per year by multiplying it by the standard U.S. school year of 180 days. The constant 180 is the standard denominator used to convert growth rates into time, representing the instructional days in a U.S. school year. The formula relies on three research-based constants: 238 for NAEP fourth grade reading proficiency, 720 as the Bloom conversion factor, and 180 for the standard school year in instructional days. When applying the formula to Michigan data, the calculation yields 1,317 school years to proficiency. However, we must first understand the critical concept of the floor. The critical innovation of the Hare Hale framework is the concept of the 0.025 standard deviation floor, which we will explore next. When growth is negative, students fall further from proficiency, resulting in a negative denominator. This breaks the formula, leading to an answer that is mathematically undefined or negative infinity. To address this, Hare and Hale assigned a proxy floor of 0.025 standard deviations to all negative and zero growth values. This floor is 1/10 of a single school year's expected growth. This 0.025 standard deviation proxy floor for negative growth is the smallest positive value that allows the formula to produce results within the scale of human comprehension. This specific value was chosen for three reasons. It preserves a positive denominator, it is vanishingly small, and it is conservative, giving the system the benefit of the doubt. Using this proxy floor, the time to proficiency for Michigan's average fourth grader is calculated to be 329 school years. This is the arithmetic consequence of 15 years of negative growth. This scene shows the calculation resulting in 329 school years, 5,925.6 instructional day equivalents divided by 4.5 instructional day equivalents per year. No prior framework handles negative growth this way. Other metrics only consider positive effect sizes or abandon extreme values. Hare and Hale view extreme values as a critical signal. The RAND study considered extreme values unstable, recommending the metric be abandoned. Hare and Hale argue that these values are the most honest representation of negative growth's impact on students. This concludes Module 2. Here are some questions to check your understanding of the Hare Hale timescale, the constants, and the problem of negative growth. Continue to reflect on these questions, including the calculation for the Michigan fourth grader and the differing interpretations of extreme values by RAND versus Hare and Hale.